In this section, we're going to take a look at partial fractions and partial fraction decomposition.
Whenever you have rational expressions, they are treated essentially as fractions. So when you add them, you can simply do so by finding a common denominator and then combining like terms. So for example, if you have 1 over x plus 2, and you wish to add to that 1 over x plus 4, you can do this by simply finding the common denominator, which here I'll do by multiplying top and bottom by x plus 2 on this expression, and multiplying top and bottom by x plus 4 on this expression. So now that the two denominators are the same, we have x plus 4 over, here you can multiply these together. X times x is x squared. That's 2x plus 4 more x. That'll give us 6x. And then 4 times 2 will give us 8. Plus x plus 2 over the exact same denominator, x squared plus 6x plus 8. And since now you have a common denominator, you can add by simply by adding along the top. So that'll give us x plus x is 2x, and 4 plus 2 will give us 6 over x squared plus 6x plus 8. Okay? So this is nothing more than addition. You find a common denominator, and then you add it along the top. What if I wanted to go backwards? What if there was a reason why instead of having one combined expression, I would rather have had the two individual expressions that were being added? Just like we have multiplication, in one direction, and we can undo multiplication by factoring. Likewise, if we take an expression like 1 over x plus 2 plus 1 over x plus 4, if we put that together, that's just called addition. But separating it, going back in the opposite direction, this is called a partial fraction decomposition. A partial fraction decomposition. So multiplication, reversing is factoring. Addition, reversing is a partial fraction decomposition. Okay, so how do we do that? Well, it turns out that it depends on what the numerator and the denominator are like. So here, instead of having a single way of doing this, we're going to separate it into a few different cases. All right, so case number 1 is what happens when your denominator is made up of distinct linear factors. So for example, let's say we want to find the decomposition, example, find the partial fraction decomposition of 9x plus 21 over x squared plus 2x minus 15. All right, so the way this is going to work is you're going to begin by factoring the denominator. And this will be the case, this will be true in all of our cases. The first step is to factor the denominator. That way we see what we're working with. The way that the denominator separates will tell us how many different factors we'll have. That tells us how many different terms we'll have. And it'll also determine how we proceed after the factorization. So the very first step is always the same. First, you're going to factor the denominator. If the numerator can be factored or if not, it doesn't really make any difference. So we don't even worry about that. Just the denominator. Here, that's going to factor as x minus 3 and x plus 5. So first, factor the denominator. And again, if the numerator can factor or not, it doesn't make a difference. Here, notice you could factor out a 3, but we're not even going to bother with that. Okay. All right, so the next thing we're going to do is we're going to now separate this. We're essentially going to pretend we know the answer and work backwards. Because here, this is the result. You have something over x plus 3 and over x minus 3 and x plus 5. What we're going to assume is that, well, if that is the result, then when we separate it, that means each of those was one of its own denominators. So here we're now going to separate this as something over the first factor of the denominator plus something else over the second factor of the denominator. If there were 3 factors, we would have plus 1 more. If there was 4 factors, plus 1 more. You'd have one rational expression for each factor of the denominator. The numerator, we don't know what it is. If we did, we'd be done. Okay, so what is the numerator going to be? We don't know. Okay, so for now, we're going to use a placeholder. A and B. We're going to have to figure out what A and B are. A and B are both constants. This would be like the number 5 and the number 3, or the number 12 and the number negative 8. Whenever you have distinct linear factors, notice the word distinct, that means these are different, and linear, meaning they're power 1. Every time that happens, your numerators will be constants. You say, well, what if they're not distinct? What if they're not different from each other? Well, then we'll have a different case. We'll have to handle that a different way. What if they're not linear? What if they're a bigger power? Well, then again, that would be a different case. We'll handle that a different way. So our second step is second. Separate the expression into as many terms, as the denominator has linear factors. So here are 2 factors, 2 terms. The numerators are constant. Okay, so now the third step, we need to figure out what those constants are. What we're going to do is we're going to simplify out by multiplying across both sides by the common denominator. When I say both sides, I mean this and this. We're not going back to this one anymore. Okay? So here we're going to say, well, let me just rewrite it as its own separate line. Let me write that as 9x plus 21 over, oh, sorry, I meant these two, not this one. X minus 3 and x plus 5 is equal to a over x minus 3 plus b over x plus 5. So here, that's my second step after I've factored, and that's my third step after I've separated. I could use the first one instead of the second one here. I could have said this one equals that one. They're all the same, but since this one's factored, it'll be slightly easier to work with. Okay? So now we're going to multiply throughout by the common denominator, which is this one right here, the biggest one. I'm going to multiply by x minus 3 and x plus 5. X minus 3 and x plus 5. And over here, x minus 3 and x plus 5. So here, these divide away, and so do these. Here, this one divides with this one, and on this expression, this one divides with this one. So our third step is to simply multiply both sides by the common denominator, which is always going to be the big one. Third, multiply both sides by the common denominator. So let's see what's left. You have 9x plus 21, the denominators are now gone, plus, here, this x plus 5 is the only one left, these two are gone, and it's being multiplied times a. Now remember, a is just a number, so you can distribute it. A times x, oops, not plus, equals, a times x plus 5 times a. Plus, and the same thing with b. Those are gone, so that b is going to distribute throughout here. That'll be bx minus 3b. But notice now that these two terms are both linear. Also notice that by this equation, we see that adding those two linear expressions gives you this linear expression. ax plus bx must equal to 9x. Or in other words, a plus b must equal to 9. Notice here that these are constants, because after all, a and b are constants. So 5a and 3b would also be constants. Combining those must give you this constant, 5a plus a negative 3b, or just say 5a minus 3b, 5a minus 3b, that's equal to 21. That's a system of equations which we can now solve. So, fourth, with the simplified equation, the one after you've gotten rid of all your denominators, you can establish a system of equations and finally, fifth, solve the system. All right, so let's solve the system of equations. Here, I can take the top equation and solve for example, I can solve for b. I can subtract the a over this way. So b is equal to 9 minus a. And now I can take that and plug it into the other equation right there. So this gives me 5a minus 3 times b, which I'm replacing with a 9 minus a, equals 21. Okay, well that's going to be, let me distribute my negative 3. That's the same as saying 5a, negative 3 times negative a, that's plus 3a. And then negative 3 times 9 is negative 27, equals 21. Combine those, it gives you 8a. Add the 27 over that way, it gives you 48. And finally divide both sides by 8 to isolate your a. 48 divided by 8, that would be 6. So there we go. We now know that a is equal to 6. But remember, b is the same as 9 minus a. So b is equal to 9 minus what we just found. In other words, it's 3. So now take that a and that b, plug it back in, and that's your result. So in the end, we get that 9x plus 21 over x squared plus 2x minus 15 is equal to a over x minus 3. We just found a is 6. Plus b, we just found b is equal to 3 over x plus 5. And that is your partial fraction decomposition. You've taken one rational expression and written it as a sum of two smaller ones. All right, go ahead and give this a try. It's going to be the same case, same kind of problem, just some different numbers so you can get a feel for it. Go ahead and, same as before, we're going to find the partial fraction decomposition. Let's go with 7x minus 4 over x squared minus x minus 12. Go ahead and pause the video, give that a try, and once you're done, go ahead and unpause and we'll go through it together. All right, so you always begin by factoring the denominator. Here that denominator factors is x minus 4 and times x plus 3. It doesn't matter what case you have, you always begin by factoring the denominator. That's what tells you what case you're in the first place. Here these are distinct, they're different, and they're linear, power 1. So what that means is I'm going to separate this into two separate fractions, one with x minus 4 in the denominator, and one with x plus 3 in the denominator. Since the denominators are linear, the numerators will be constant. So now it's just up to us to find that constant. I can now multiply on both sides, here and here, by the common denominator. So I'm going to multiply by x minus 4 times x plus 3. Multiply over here by x minus 4 times x plus 3. And multiply over here by x minus 4 times x plus 3. So that will give me my next step down here. If I multiply this expression in blue by this common denominator, my entire denominator goes away, and I'm simply left with 7x minus 4. No more denominator. If I multiply this in blue by this common denominator, the x minus 4 is divided away, and I'm left with a times x plus 3, which I can distribute the a. That's a times x is ax, and a times 3 is 3a. Plus, well, if I do that over here, the x minus 3 and the x minus 3 divide away, so we're just left with the x minus 4 there, and I can distribute the b to give me bx minus 4b. But now I note that I can establish a system of equations because ax plus bx must equal to 7x. Whatever those two numbers are, it could be 5x plus 2x will give me 7x. Or maybe 1x plus 6x would give me 7x. Or maybe 10x and negative 3x would give me 7x. Whatever those two numbers are, together have to give me 7. Okay, so a plus b must equal to 7. And likewise, the constants, notice those don't have any x's, they're just numbers. Those have to add up to give me negative 4. So 3a minus 4b is equal to negative 4. And with this system, we can now find our a and our b. Here, I can solve for one of my variables. I'm going to solve for b. That's just a personal choice. I usually solve for b. You can solve for a. Doesn't make any difference. And now that we know what b is, we can take that and plug it in right here. So that's going to give us 3a minus 4 times the b we just found, which is 7 minus a, is equal to negative 4. That's going to be 3a minus 4 times 7 is minus 28. And minus 4 times minus 1 is plus 4. Minus 4 times minus a is plus 4a is equal to negative 4. And we distribute the minus 4 here and here. You can combine those. 3a plus 4a will give us 7a. And then if you add the 28 over this way, you're going to have 28 minus that 4 will give us 24. Here, we can divide both sides by 7. And in this case, it doesn't divide evenly. That's fine. No one ever said it had to divide evenly. It's a constant. It can be a fraction. Let's see, does that reduce? No, it didn't even reduce. Okay, so that's our value of A. Oh, but B is 7 minus whatever A is. Okay, so B is equal to 7 minus 24 over 7. So that will give us what? 25 over 7. And those are our results. So in the end, that means 7x minus 4 over x squared minus x minus 12 is equal to, our A is 24 over 27. Oh, sorry, it's 24 over 7, not 27, over x minus 4, plus our B, well, that's going to be 25 over 27. I keep saying 27. 25 over 7 over x plus 3. And the way fractions work, of course, you don't usually have a fraction within a fraction, so you can take this denominator and bring it down into the overall denominator. So here you can write that as 24 over 7 times x minus 4 plus 25 over 7 times x plus 3, like that. Or you can even distribute the 7 to give you 24 over 7x minus 28 plus 25 over 7x plus 21. And really, any of these would be a perfectly acceptable answer. These are all good partial fraction decompositions for that expression there. So this is another example of case number 1, where your denominator is made up of distinct linear factors. Okay, so now let's take a look at the next case, case number 2. And here I'm labeling these as case 1 and case 2 and case 3. In different books you may have them denoted as, in a different order. So there's nothing inherent about this one being case number 2. This is just the way I'm expressing it here in this lecture, in this video. So case number 2 is what happens when you have repeated linear factors. So here the factors are still linear, but they're not distinct. They appear 2 or more times. Repeated linear factors in the denominator. All right, so for example, let's consider something like x squared minus 6x plus 3 over, and here they actually do us a favor of having this already factored for us, x minus 2 to the third. So here we can actually skip that first step. Usually our first step would be, okay, factor this. But here they went ahead and factored it and said, okay, x plus, the denominator is x minus 2 times x minus 2 times x minus 2. So here we have repeated linear factors, right? They're the same one over and over again. All right, so when that happens, here's how we're going to split this up. First of all, we're still going to have as many rational expressions as we have factors in the denominator. Here there's 3 factors, right? Even though they're all the same, you have 3 of them. X minus 2 times x minus 2 times x minus 2. Okay. What will now differ will be the way we write the denominators. Whenever you have a repeated linear factor, your first rational expression will have 1 copy of that linear factor, like this. The next one will have 2 copies of that linear factor. You can write that as x minus 2 times x minus 2, or as I'm going to do, I'm going to write it as x minus 2 squared. And then the next one will have another copy of our linear factor. So you can write it as x minus 2 times x minus 2 times x minus 2, or as I'm about to do here, you can write it as x minus 2 to the third. So basically you're counting up. You're saying, okay, first power, second power, third power. If this had power 5, well, then you go 4 and 5. If it had power 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll have as many rational expressions as you have factors in the denominator. Here, each one will have the same denominator with a different power, starting from the first one all the way up to full power. So here, your first step was to factor, as always. Here, we were already given a factorization, so we were able to skip that. But first, factor the denominator. Second, write as many terms as you have factors in the denominator. Each with a different power, from the smallest to the largest, power 1, power 2, power 3. Your numerators are still going to be constants. Even though these look like they're a linear, a quadratic, and a cubic, here what we have is we have a linear factor that just happens to be repeated several times. So even though this is not linear anymore here, we're still going to treat it the same way as we did the previous case. So your numerators are still constants. All of them. Not just this one, but all of them. All right. And so now the rest of it is going to look the same as we've had. We're going to multiply by the common denominator, and we're going to solve for a. Right? So our next step here is we're going to multiply everything by a common denominator. That's x minus 2 times x minus 2 times x minus 2. And same thing for this one. And same thing for this one. And same thing for this one. Here, these 3 divide away those 3, so no more denominator. Here, those 3 divide away those 3. Here, 2 of those divide away 2 of those. And here, 1 of those divides away 1 of those. So, third, multiply by the common denominator. Okay, well, let's see what's left after we've done that. On this side, we have x squared minus 6x plus 3. Note there is no more denominator. It's been divided away. Over here, we have, well, we can multiply those. 2x, sorry, not 2x, x minus 2 times x minus 2. We can distribute that. That's x squared. That's minus 2x minus another 2x, that's minus 4x. And then minus 2 times minus 2 is plus 4. So multiplying those two together gives me x squared minus 4x plus 4. And it's being multiplied by an a. Okay, so it's going to give me ax squared minus 4ax plus 4a. All of those get multiplied by an a. Plus your b. Now, notice those are all gone, so it's just b times x minus 2. Okay, so b times x times, and b times minus 2. bx minus 2b. And then here, everything's gone except for that c. So that's just plus c. Okay, so we've gone ahead and multiplied by the common denominator. We've gotten something that looks like a polynomial. Okay, at this point, it now looks very familiar, much like all the other cases. Fourth, you're going to do the same as before. Oops, wrong page. You're going to do the same as before. Once you've cleared that, you're going to find this system of equations. So with fourth, we're going to establish the system of equations. Same as with case number 1. And finally, you're going to solve. So notice this is very similar to case number 1, the main difference being what your denominators look like. All right, before, the denominators were all, when you had a distinct linear factor, all of your denominators, each one had its own chance to be the denominator, and there were never any powers. So when they repeat, okay, well then you're going to have to repeat the factors in the denominator one at a time. 1 and then 2 and then 3. Otherwise, everything looks about the same. We're going to now set up a system of equations and then solve. So let's see here. We have an ax squared, and that's the only squared term there. Okay, well, ax squared has to equal to x squared. Oh, well, that makes things pretty easy. That means a has got to be equal to 1. Okay, well, that makes it easy. A equals 1. Okay. What other system of equations do I have? I have, here is a linear term because it's got an x, and there's a linear term because it's got an x. So negative 4ax plus bx, that's got to be negative 6x. Linear plus linear has to give me the linear term. So the negative 4a plus the b have to be negative 6. Negative 4a plus the b have to equal to negative 6. And finally, this is a constant. There's no variable. It's just two numbers multiplied together. That's just a number. And that's a constant. And that's a constant. And all the constants have to come together to give me that constant. So that's going to give me 4a minus 2b plus c. 4a minus 2b plus c. And that's going to equal to 3. 4a minus 2b plus c. All right, so now we can solve that system of equations. We know what a is already. That was nice. So you can always plug that into this equation. This equation, negative 4 times a, negative 4 times 1 is just negative 4, plus b is equal to negative 6. You can add the 4 over to this side, and that solves for your b. b is equal to negative 2. Okay, now you know your a and your b, so now plug those in right here. That's going to be 4 times a, 4 times 1, minus 2 times b, which is a negative 2, plus c equals to 3. 4 times your a, minus 2 times the b you just found, plus c equals to 3. Okay, well that's 4, and double negative makes that another 4, so that's 8. So I can subtract the 8 over this way. That leaves the c on its own. And here, 3 minus this 8 will be a negative 5. And there we go. We found the values of a, b, and c. So that gives us our answer. X squared minus 6x plus 3 over x minus 2 to the third power. That's going to equal to a, which is 1, over x minus 2, plus b, which is negative 2. Now here you can say plus a negative 2, or you might actually be better to just say minus 2. So if that's a negative, you can say plus a negative, and that's fine. But you might just be better off just saying negative. So minus 2 over x minus 2 squared. And then plus c. Oh, but c is also negative, so I may as well just write that as minus 5 over x minus 2 to the third. And that is our partial fraction decomposition. Instead of having one big expression with one big denominator, we've separated into, this time, 3 rational expressions, each of which has a constant in its numerator. And that's our result. Okay, so go ahead and give this a try. You're going to find the partial fraction decomposition. Of, let's say, 6x minus 11 over x squared minus 2x plus 1. Notice here this one is not factored for you, but you can factor that one, and you will find that it is a set of repeated linear factors. So remember your steps. Factor the denominator. In this case, it hasn't been done for you, but that's a simple one to factor. Then write as many terms as you have factors in the denominator. In this case, I had 3 factors, so I wrote 3 terms. If you had 4 factors, you write 4 terms, whatever it takes. Multiply by the common denominator, establish your system of equations, and finally solve. So go ahead and give that a try. Pause the video and give yourself the time you need. Once you have your result, you can unpause the video and we'll go through it together. All right, so let's give this a try here. This is equal to 6x minus 11 over. When you factor this, that's x minus 1 times x minus 1. So here that is a repeated linear factor. Right? They're linear, but there's two of them. Okay, so the way that's going to separate is you're going to have x minus 1 to the first power first, and then x minus 1 to the second power. If there were any more, you'd keep going. Third, fourth, fifth. Oh, but second power is the most you have, so you can stop there. Even though there's a square here, the reason the square is there is not because it's a squared factor, but rather because it's a linear factor that happens to repeat. So here we still treat this as if it were a linear factor in our denominator, and so our numerators are still constants. If ever you had a square here that wasn't because you had a linear factor, that'll be case number 3, and we'll see that in our next examples. All right? So now we have this, which means we can multiply across by our common denominator. So here if I multiply by x minus 1 times x minus 1, that multiplies this term by x minus 1 times x minus 1, and same thing with this one. You know, technically I should, since all of these are equal, I should multiply this one by x minus 1 times x minus 1. But in any event, we really just care about these two. Here these completely divide away, leaving you 6x minus 11. Here, only one of these divides away. That leaves you a times x minus 1. Well, I can distribute that. A times x is ax, and a times negative 1 is negative a. And then here, both of these divide away, and you're left with just your b. So this one's a little shorter than the previous one, and that's okay. They'll have different lengths depending on what the numerator and denominator are. Notice here, this linear term must match that linear term. It's the only one like that. So ax must equal to 6x. That means a must equal to 6. Here my linear terms should equal to the linear result. Okay, so negative a plus b equals negative 11. Negative a plus b equals negative 11. So now we know the value of a is equal to 6, and that can simply be plugged in right here to give us negative 6 plus b equals negative 11. So this gives us negative 6 plus b is negative 11. Finally, add your 6 over to the other side, and that will give you b is equal to negative 5. So in the end, we have our results where a is equal to 6. So that means 6x minus 11 over x squared minus 2x plus 1 is equal to 6 over x minus 1. And then here you can say plus a negative 5, or more simply, you can just say minus 5 over x minus 1 quantity squared. And that is our partial fraction decomposition. One thing to note is that our case number 1 and our case number 2 don't have to be mutually exclusive. You can have some which mix and match the two cases. For example, let's say that you have, I guess I should give the directions here. Find the partial fraction decomposition. Of 3x squared plus 49 over x times x plus 5 quantity squared. Like this. All right. In this case, you'll notice you have repeated linear factors, but they don't all repeat. So here, this is like case number 1 because these are different. Oh, but this is like case number 2 because they repeat. So in that case, you're going to have a mix of both. Here, I'm going to write this, before I even start the decomposition, I'm going to go ahead and write this out as 3x squared over 49, plus 49, over x times x plus 7 times x plus 7. So that's sort of a mix of both. Without this one, that would be case number 1. Without this one, that would be case number 2. Put them all together, well, that's kind of a mix of both. Okay, so how does this work? Well, whenever you have distinct linear factors, what happens is you have the first factor gets a chance to be a denominator, and then the next factor gets a chance to be the denominator of its own rational expression. Oh, but now this one repeats. Okay, well, we know that when something repeats, you write it once, and then in the next one, you have the denominator with the same factor with a higher power, like that. So if you have, for example, x plus 7 to the third power, well, then you'd have one more of those. All right, so here that's a mix of case number 1 and case number 2. But in both case number 1 and case number 2, your numerators are constants. So in this case, all three of these are going to be constants anyway. So that is a mix of both situations. Now, once we know what case we're in, once we've separated everything out, now we proceed to solve for our constants. The good thing is that in both case number 1 and case number 2, the way we proceed after this initial setup is exactly the same. We're going to multiply both sides by the common denominator and then simplify. So here I'm going to multiply across by x times x plus 7 times x plus 7, x times x plus 7 times x plus 7, x times x plus 7 times x plus 7. It sounds like this. I wish my problems weren't so big, but we'll get through them eventually. And finally, x times x plus 7 times x plus 7. All right, so of course this divides away all of this. Semicolon here, right? This divides away all of this, regardless of which form you have it in. Here, this x divides that x, but those two are left. Here, this x plus 7 divides that x plus 7, but those are left. And here, both of these x plus 7s divide away both of these x plus 7s, leaving you just your c and your x. So what that gives us is the numerator, 3x squared plus 49. Note your denominator's gone. That's equal to, well, let's see, x plus 7 times x plus 7. That's x squared plus 14x plus 49. But that's getting multiplied by a. Okay, so that's going to be ax squared plus 14ax plus 49a. Multiply that together, but then don't forget the a. Here, b times x is bx. And if you multiply that bx times x plus 7, bx times x is bx squared. And bx times 7 is, well, 7bx. And finally here, c times x is cx. Okay. We have some quadratic terms. We have an ax squared and a bx squared. And if you combine those, that has to give you 3x squared. Those are the only squares around, so together they have to form that 3x squared, which means the a plus the b must equal to 3. Your linear terms, that's 14ax, that's 7bx, and that's cx. All of those are linear. They have an x to the first power. Notice there's no linear term over here, which means all of these have to cancel out. So if you take the 14a and the 7b and the c, those all have to add up to 0. If you combine this linear term with this linear term and this linear term, all three of them add together, we're not supposed to have any linear term. So that adds up to 0. And finally, this linear term, this constant term must match this constant term. So we have 49a is equal to 49. All right, well, this last one's easy. There's only a single variable. There's only a single unknown. We can divide both sides by 49, and we get a equals to 1. Okay. Since a is equal to 1, we can plug that into the top equation. So that's going to now be 1 plus b. That's equal to 3. We can subtract the 1 over to the other side, and that gives us b is equal to 2. But now we know both a and b, so we can plug that into this middle equation. That's 14 times 1 plus 7 times 2 plus c is equal to 0. Okay, well, 14 times 1 is 14. And 7 times 2 is also 14. 14 plus 14 is 28. And if these have to give you 0, that 28 must be met with a negative 28. So that means C is equal to negative 28. And so that gives us our result. Here our expression 3x squared plus 49 over x times x plus 7 squared is equal to a, which is 1 over x, plus b, which is 2 over x plus 7, plus c, which is negative 28. You can say plus a negative 28, or may as well just say minus 28. Both are fine. Minus 28 over x plus 7 squared. So do note that you may have situations where your cases are mixed. Here that's a mix of case 1 and 2. And that makes us happy. Finally, our last situation comes in when you have nonlinear factors. Now here you might say, well, that's quadratic, right? Well, yes and no. Yes, that is quadratic because there's a square there. But the reason it's a quadratic isn't because there was a quadratic factor, but because there was a repeated linear factor. But what happens when the factor is quadratic in and of itself? As in, it's not a repeated linear factor, but rather you just had a square because that factor has a square. So that's our case number 3, and that is what happens when we have what are called irreducible quadratics. You may remember from college algebra that whenever you have a quadratic, you can factor it into 2 linear factors. However, sometimes it requires you to use complex numbers. So recall, if you have something like x squared plus 2x plus 1, okay, that factors as x plus 1 times x plus 1. Okay, so that's a repeated linear factor, but they're linear. If you have something like x squared minus 1, okay, well that factors as x plus 1 and x minus 1. And those are distinct linear factors. So case number 1 and case number 2. However, you may remember something like this, where the only way to factor this was to use a complex 0. Have a complex value in your factors. Because, of course, the zeros of this are complex numbers. So can you factor that? Sure, but it factors as x plus I times x minus I, which is not something we're prepared to deal with. So this would be called an irreducible quadratic. When we say irreducible, I don't know how to spell, that should be quadratic, there we go. When we say irreducible, we don't mean it's not reducible at all. We mean it's irreducible when it comes to real numbers. Here, we would have to resort to complex numbers to reduce it. So here, when we say irreducible, we mean using real numbers. We can reduce it if we're allowed complex numbers, but we're not going to allow that. So irreducible using only real numbers. Okay. Now, in college algebra, you learned one other thing, and that's that if it's degree 3 or higher, you can always factor it. You can factor down into linear or quadratic factors. And maybe that factorization isn't easy to come by. Maybe the factorization takes a lot of time, but you can always do it. If you have a cubic, you can always factor it into either 3 linear factors or 1 linear and 1 irreducible quadratic. If you have a quartic equation, power 4, you can either reduce it into 4 linear factors or 2 linear factors and an irreducible quadratic, or maybe 2 irreducible quadratics. But no matter what you have, you can always reduce things down into either linear, irreducible quadratics, or a combination of those. Which means that you really only ever need case 1, case 2, or case 3. Either everything's linear and separate, linear and repeated, or not linear, which means quadratic. So let's consider an example where we have an irreducible quadratic, and let's see how that is handled. So for our first example, let's consider wanting to find the partial fraction decomposition of 5x squared minus 9x plus 19 over x minus 4 times x squared plus 5. Now here we note that we have a linear expression, but we also have an irreducible quadratic. The only zeros of this are complex numbers. You would have either plus or minus the square root of 5 times I. Those are the only zeros of something like this. So that means that you couldn't reduce this any further without resorting to complex numbers. So we call that an irreducible quadratic. All right, so how does that work? Well, it's going to work in a way that's similar to our first two cases. Here we have two factors. You say, well, they're not linear. Oh yeah, but they're still two factors, which means we're going to separate this as the sum of two rational expressions. Okay, so far that looks the same as case number 1 and case number 2. Here, this first factor will get a chance to be its own denominator, and the second factor will get a chance to be the denominator of its own expression as well. Okay, so far that looks the same. That's going to be one denominator, that's another denominator. Here's where it's different. The numerators. If your denominator is linear, whether it be a distinct linear expression or a repeated linear expression, right? Distinct, different from the others, or repeated, your numerator is always a constant. But if your denominator is a irreducible quadratic, your numerator will not be a constant. It'll be linear. It'll be power 1. So it'll have maybe an x term and maybe a constant. I say maybe because it's possible that this can be 0, or it's possible that this can be 0. So you might end up with just a plus c, or you might end up with just a bx, or maybe you'll have both. So that's the difference here. In the situation where you have an irreducible quadratic, note the numerator of an expression with an irreducible quadratic in the denominator is going to be linear. Some number times x plus some number. Here I already used a, so I went with b and c. Let's say I had already used a and b, then I'd do cx plus d, just whatever numbers I haven't used yet. That's the main difference. Here, this is linear, so its numerator is constant. This is quadratic, so its numerator is linear. A simple way to remember that is basically the power is going to have 1 degree less. Power 1, power 0. Power 2, power 1. Everything else about this is exactly the same as case number 1 and case number 2. We're going to multiply by the common denominator and solve. So note that the differences in our three cases are not how we solve, but how we set things up. Once things are set up, the solution is the same. Multiply by the common denominator, set up your systems of equations, and then solve. So let me go ahead and do that. Let's multiply both sides of this equation by x minus 4 and x squared plus 5. Same thing over here, x minus 4, x squared plus 5. And same thing over here, x minus 4 and x squared plus 5. Here, all of this divides away with all of this. This one divides this one, and this one divides this one. So what's left is 5x squared minus 9x plus 19. That's the only thing left of my first expression. Okay. Is equal to, here we're going to take that a times the only thing left, x squared plus 5. If we distribute the a, that'll give us ax squared plus 5 times a, plus, if we multiply this out, bx times x is bx squared. Bx times negative 4 is negative 4bx. c times x, that's going to be cx, and c times negative 4 is negative 4c. Like that. So we've distributed this out. That gives us those 4 terms. We've distributed this out. That gives us those 2 terms. And here everything divides away, leaving us just the original numerator that we started with. So now we can set up our system of equations. Notice I have a quadratic expression there, and those two would have to come together to give me 5x squared. Ax squared plus bx squared must equal to 5x squared. So a plus b must equal to 5. My linear terms have to come together to give me my linear term. Negative 4bx plus cx must equal to negative 9x. So that means the coefficients negative 4b and c, negative 4b plus c, that has to equal to my negative 9. And finally, my constants, 5a and negative 4c, must equal to 19. 5a minus 4c, that's got to equal to 19. So now we have a system of equations which we can solve to get our result. Here, I'm going to go ahead and solve this by starting with the top equation. I'm going to solve for one of my variables. I think I'll solve for b. b is equal to 5 minus a. So now I can take that and plug it into the second equation, which will now give me negative 4 times b, and I'm going to replace the b with 5 minus a, plus c equals to negative 9. Okay, so that's gone in there, and now I have this new equation. I can distribute my negative 4, so negative 4 times negative a, that's positive 4a, and negative 4 times 5 is negative 20, which I think I'll add to this side. So let me get rid of the minus 20 by adding 20 over here. If I take 20 minus that 9, that'll give me 11. And then that plus c stays right where it was. So 4a plus c, minus 20, I add this way, plus 20. Negative 9 plus 20 is 11. So now, these top two equations have come together to give me a new equation. 4a plus c equals 11. And this bottom equation gives me 5a minus 4c equals 19. So now instead of having 3 equations that have 3 variables, now I have just 2 equations with 2 variables. And that should be easier to solve. I had my 3 equations with 3 variables. So now, let me use this top equation. We solve for c. That's going to be c equals 11 minus 4a. And I'm going to take that c and plug it in right there. That'll give me 5a minus 4 times the c we just found, which is 11 minus 4a, equals 19. That's going to give me 5a. Negative 11 times 4, that's negative 44. And then negative 4 times negative 4a, that's positive 16a. That's equal to 19. I can combine those. That's 16a plus 5a. That gives us 21a. And then I can add my 44 over this way. So 19 plus that 44 will give me 63. I can divide both sides by 21 now. That is mean a is equal to 3. There we go. So now we know what a is. A is equal to 3. Oh, but we know that b is equal to 5 minus a. So that means b is equal to 5 minus the a we just found, 5 minus 3. Okay, so that means b is equal to 2. And we know that c is equal to 11 minus 4 times a. So that gives us c equals to 11 minus 4 times a, 4 times 3. And that's 11 minus 12, which is negative 1. So that gives us our result. In the end, it turns out that our 5x squared minus 9x plus 19 over x minus 4 times x squared plus 5 That's going to equal to our a, well, that was 3. So that's 3 over x minus 4 plus our b was 2 and our c was minus 1. So 2x plus a negative 1, or just 2x minus 1, over x squared plus 5. Note that there are 2 constants here. It is possible that one of these might end up as a 0, so it's possible sometimes you'll get just something like 2x over x squared plus 5, or in other situations you might just get something like negative 1 over x squared plus 5, and that's fine. It's possible one of these ends up being 0, but in this case they both ended up being something non-zero. And so we end up with our result, and that makes us happy. All right, so go ahead and give this a try. You're going to find the partial fraction decomposition of, let's go with this one, 3x minus 5 over x cubed minus 1. So you're going to begin by factoring out your denominator. Here they have not done that for you, so we're going to have to do the factorization ourselves. And once you factored it out, you'll know you will have an irreducible quadratic. I'll tell you that much ahead of time. So go ahead and give this a try. Pause the video. Give yourself the time that you need, and once you're done, you can unpause and we'll go through it together. All right, so here, that's the difference of cubes. Recall that if you have something like a cubed minus b cubed, cubed, that factors as a minus b times a squared plus ab plus b squared, like that. And that's precisely what we have here. That's x cubed minus 1, which is the same as saying 1 cubed. So that would factor out as a minus b, so x minus 1, times x squared plus the x times the 1, which is just 1x, plus the square of 1, which is still just 1. This cannot be factored any further. Here, anytime you have either the sum or difference of cubes, this remaining expression is an irreducible quadratic. If you doubt that, go ahead and try to find zeros of this. Use the quadratic formula if you like, and you'll get complex zeros. So here, this cannot be reduced using any real numbers. Okay, so since that cannot be reduced using any real numbers, that's an irreducible quadratic. So that means that this expression would separate as something over x minus 1 plus something else over x squared plus x plus 1. Since that denominator is linear, your numerator would be constant. And since this denominator is quadratic, the numerator would be linear. Okay? So now we can solve for a, b, and c. We're going to do that by multiplying throughout by x minus 1 times x squared plus x plus 1. And same thing over here, x minus 1 times x squared plus x plus 1. And same thing on this side, x minus 1 times x squared plus x plus 1. And finally over here, x minus 1 times x squared plus x plus 1. Here, of course, these just divide all the way out since that is the denominator. Here, some of these divide away and some are left. Here, these two divide away, leaving you your a times your quadratic. And here the quadratic divides away, leaving you bx plus c times your linear term, your linear factor. So here that's going to give us 3x minus 5, that's your numerator, equals, well, here you can distribute your a to give you ax squared plus ax plus a. And over here, you can distribute these. Bx times x is bx squared. Bx times negative 1 is negative bx. c times x is cx, and c times negative 1 is negative c. So we distribute these 3 to give us those 3, and we distribute out these 4, giving us those 4. All right. Note here that your quadratics must cancel out because there is no quadratic term here. So ax squared plus bx squared, the a and the b must add up to 0 because there is no x squared term here. So our system of equations begins with a plus b must equal to 0. Ax squared plus bx squared gives you no x squared. So the a and the b must give you nothing. Our linear terms, we have a ax, we have a negative bx, and we have a cx, and those add up to 3x. So a minus b plus c is equal to 3. A minus b plus c is equal to 3. And finally our constants, we have a constant here, and we have a constant right here. A minus c must equal to negative 5. A minus c is equal to negative 5. Okay. All right, so we can solve for both b and c in terms of a. In this top equation, so here's our system. Our top equation, we can say that b is equal to negative a. I can subtract the a over this way. In the bottom equation, I can say c is equal to, I can add the c over this way and then add the 5 back this way. So a plus 5 would equal to c. So we can solve for b in terms of a. We can solve for c in terms of a. And then we can throw both of those into the middle equation. And the middle equation is now a minus your b, which is a negative a, plus your c, which is an a plus 5. And that's got to equal to 3. A minus b, which we already found right here, plus c, which we found down here, has to equal to 3. Okay, so minus and minus, that's plus. So a plus a, that's 2a, plus another a, that's 3a. 3a. And then there's a 5 right there. Plus 5 is equal to 3. You can subtract 5 from both sides. That'll give you 3a is equal to negative 2. And then divide both sides by 3, and you find that a is the fraction negative 2 over 3. But since you now know what a is, you can find b and c. After all, we know that b has to equal to the opposite of a, or in other words, it's the opposite of negative 2/3. In other words, it's positive 2/3. That's your b. And we know that c has to be whatever a is plus 5. Well, a is negative 2/3. And if you add 5 to that, it's going to give you 13/3. And so now we have our decomposition. We found our a, our b, and our c, which means that 3x minus 5 over x cubed minus 1 must equal to a, which we find to be negative 2/3, over x minus 1, plus our b, that's 2/3, x, plus our c, which is 13/3, over x squared plus x plus 1. Now, we don't really ever leave complex fractions, but notice that they all have the same denominator, so you can simply force that denominator down along with the other denominator. You can write this as negative 2 over 3 times x minus 1. This denominator joins that denominator. Plus, here they have a common denominator of 3, so let me put that in the denominator, along with the x squared plus x plus 1. And if you take the denominator and put it down there, all that's left up here is a 2x plus 13. And of course, you can always distribute the 3 here, and that'll give you negative 2 over 3x minus 3 plus 2x plus 13 over 3x squared plus 3x plus 3. And really, any of these would be acceptable. as your partial fraction decomposition. And that makes us happy. All right, and finally we have case number 4. We've seen distinct linear factors, and then we've seen repeated linear factors. Well, now we've seen distinct quadratic factors. Well, what happens when we have repeated quadratic factors? What happens when you have something like this squared or cubed or something of that nature? So that's case number 4. What happens when you have repeated irreducible quadratic denominator factors? Repeated irreducible quadratics. So, for example, let's say we wish to find the partial fraction decomposition of the expression x squared plus 2x plus 3 over x squared plus 4 squared. So here you have two factors, but they're quadratic, and that can't be reduced using only real numbers. Not only that, but even though you do have two factors, they're repeated. After all, that can be written as x squared plus 4 times x squared plus 4. So those are repeated irreducible quadratic factors in our denominators. So in that case, what's going to happen is we're going to, well, there's two factors, which means we're going to have two different rational expressions that this splits into. And this is going to look a lot like case number 2. When you have repeated quadratic factors, what's going to happen is you're going to write one on its own, and then the next one will have a bigger power than the previous one, like this. So you're going to take one of the factors on its own and then two of them. If this was x squared plus 4 to the third, well, then you'd have x squared plus 4, x squared plus 4 squared, and then the next one would be x squared plus 4 to the third. If you had 10 of these, well, then you'd have first power, second power, third power, fourth power, all the way to 10th power. Okay? So this does look an awful lot like the second case. Okay? Now, this is an irreducible quadratic, which means that the numerator should be a linear expression, ax plus b. Note here that that's going to also be a linear expression, because just like with the linear case, even though it has a bigger power here, it's not really a bigger power. It's just a repeated case of this smaller power. So here, this numerator will still be linear, cx plus d. Something like that, yeah? Okay, so now that we have that, now we can proceed to solve. Here we're going to multiply everything by x squared plus 4 and x squared plus 4. And then on this side, same thing, x squared plus 4 times x squared plus 4. And over here, same thing, x squared plus 4 times x squared plus 4. Note here that all of these divide all of these here. This one divides one of these, but there's still one left. And then both of those will divide both of those. So in the end, you're left with your original numerator, your x squared plus 2x plus 3 is equal to, okay, well, we can multiply this part out. Ax times x squared, that's ax cubed. Ax times 4, that's 4ax. B times x squared, that's bx squared. And b times 4, well, that'd be 4b. And then over here, all of this divided away, so really we're just left with this part right here. This doesn't multiply by anything, you just leave it as cx plus d. Everything else divided away. So this does look an awful lot like case number 2. If it repeats several times, you write it with that many separate expressions. The first one with this as the denominator with power 1, the next one with power 2, and if this has any bigger powers, you keep going, 3, 4, 5 until you're done. And then the numerator will have one less power than the denominator. Here, yes, this is a quartic, 4th degree, but really it's not. It's just the fact that this quadratic repeated. So here we treat this as if it were a quadratic, which means the numerator will be linear. And so now we can solve our system of equations. Here, notice that you have a cubic term, which you're not supposed to have. So that means that ax cubed must equal to 0. Okay, so then a's got to be 0. That makes that simple. That's already one of our answers. Let's see here. Our quadratic term, there's only one of those. I have a bx squared, and that's got to equal to 1x squared. Okay, so b's got to equal to 1. That one's straightforward enough. We have linear expressions. Here's one linear expression, cx, and here's another one, 4ax, and those have to add up to 2x. So 4ax plus cx is 2x. That means 4a plus c must equal to 2. 4a plus c must equal to 2. And our constants, we have a 4b plus a d. That's got to be 3. 4b plus a d. That's got to be 3. Oh, but these are made simple by the fact that we already know a and b. This first equation, 4a plus c is equal to 2. We know a is equal to 0. So 4 times 0 plus c is equal to 2. And since 4 times 0 is 0, all you're left with is c is equal to 2. Over here, we know b is equal to 1. Okay, so that's going to be 4 times 1 plus d is equal to 3. Okay, well then, to get the d by itself, subtract the 4 over this way. 3 minus that 4 gives you d equals to -1. And that's it. That gets us our result. So our partial fraction decomposition x of x squared plus 2x plus 3 over the repeated irreducible quadratic factor x squared plus 4 squared is going to equal to, notice your a was 0. I mentioned this earlier. It's possible that your term might have one or you might have one or the other missing. And here that's what we have. There is no a, but there is one b. So here the numerator is just b. There's no ax term. So that's going to be 1 over x squared plus 4 plus, now here there is both a c and a d, so it'll be 2x minus 1 over x squared plus 4 quantity squared. And there we go. There is our partial fraction decomposition, and that makes us happy. This prepares you for problems in calculus. Much like factoring is often used in algebra, when you have a big complicated polynomial and you want to separate it into smaller polynomials to help you solve things. In calculus, there will be times where you have large complicated rational expressions, and there are things you're going to want to do with that that'll be made simpler by having the sum or difference of smaller, simpler rational expressions. So this will serve the same purpose as factoring. It will serve to take something large and complicated and separate it into 2 or more smaller expressions that are easier to work with. Finally, the last thing we want to mention is that in every one of our cases so far, in every one of our problems that we've seen, in every situation, your numerator is always smaller in degree than your denominator. Notice that is 4th degree if you were to multiply it out, and that's 2nd degree. Over here, that's 1st degree and 3rd degree. Over here, we had 2nd degree and 2nd plus 1, a 3rd degree. Well, here you have second and third degree. In every situation we've had so far, you have had a quadratic over a cubic. In every situation, your denominator has had a bigger power than your numerator. If that doesn't happen, all you have to do is divide. This isn't really even a separate case. It's just, we shouldn't have an improper fraction. We shouldn't have a situation where the power of the numerator is greater than the power of the denominator. So if and when that happens, we simply divide. So for example, let's say, and here the directions read the same. We're going to find the partial fraction decomposition. Of x to the power 4 plus 2x to the power 3 minus 4x to the power 2 plus x to the power 1, or you can just say plus x, minus 3 all over x squared minus x minus 2. Okay. Notice that the power of the numerator is not smaller than the power of the denominator. If the power of the numerator is equal or greater, divide first. Note, if the power of the numerator is greater than or equal that of the denominator, divide first. So here we're going to just divide. We're not even going to worry about partial fraction decomposition just yet. Remember how long division of polynomials works? It works pretty much the same as long division of regular numbers works. Your numerator goes in the box, your denominator goes on the outside, x squared minus x minus 2, and then you simply divide from front to back. Here x squared goes into x to the 4th x squared times, and if you take x squared and multiply by this, that gives you x to the 4th, that's minus x to the 3rd, and that's minus 2x squared. And then you subtract all that away. So here, x to the 4th minus x to the 4th, that cancels out. The first term should always go to 0. If not, you did that wrong. Here, that's minus a minus, so that's going to be plus. 2x to the 3rd plus x to the 3rd, that's 3x to the 3rd. And same thing here, minus a minus, that's a plus. So that's going to be negative 4x squared plus 2x squared is negative 2x squared. Right, negative 4 plus 2 is negative 2. Bring down the next number. And we do it again. If you take 3x to the 3rd divided by x squared, that's going to be a positive 3x. 3x times x squared is 3x to the 3rd. 3x times negative x is negative 3x squared. And 3x times negative 2 is negative 6x. And you're going to take that whole thing and you're going to subtract it. Once again, every time you subtract, that first set of terms should go to 0. If not, you did something wrong. So here, 3x to the 3rd minus 3x to the 3rd, that's definitely 0. Here, that's a double negative, which makes that a plus. So that's positive 3x squared minus 2x squared is going to be 1x squared. And same thing here, double negative makes that a plus 6x plus another x. That'll give us plus 7x. And then drop your minus 3 one more time. Let's divide. X squared goes into x squared once. So that'll be a plus 1. And then that's going to be 1 times all of this stuff. That's x squared minus x minus 2. And then take that whole line and subtract. X squared minus x squared, that number minus itself, that's 0. And again, at every stage, that first term should go to 0. If not, we did it wrong. Here we have minus a minus, so that's plus. 7x plus x, that's 8x. And then negative 3 minus a minus, okay, negative 3 plus 2 is negative 1. So that means that our expression can be written as x squared plus 3x plus 1 plus your remainder over your divisor. And this is just a reminder of long division, as we've seen since algebra, like this. Notice that now this is a polynomial. It's not rational. So you don't have to worry about a partial fraction decomposition here. It's already the sum of stuff, this plus this plus this. All that's left now is to perform the partial fraction decomposition on this part. So note, if the power of the numerator is greater than or equal to the power of the denominator, divide first. Then perform the decomposition on the remaining rational expression. The polynomial part, that's already the sum of stuff. So we just worry about this part of the remaining rational expression. Just like that. So really, we're just focused on this part now. Okay, so let's go ahead and do that. 8x minus 1 over x squared minus x minus 2. This separates out as 8x minus 1 over x minus 2x plus 1. That's a factorization. And since those are distinct linear terms, we wrap things up going back to case number 1. So here that's going to be a over x minus 2 plus b over x plus 1. We'll multiply everything by the common denominator. Over here, that completely gets rid of your denominator. And over here, it gets rid of your denominator, although it does leave you an extra factor in each of these terms. So that's going to give us our original numerator, 8x minus 1, is equal to a times x plus 1. We can distribute the a. That gives us ax plus a. Plus b times x minus 2. We'll distribute the b, giving us bx minus 2b. 2b or not to be. Yeah? That's the question. So let's find the answer. ax plus bx must equal to 8x. Oh, so then a plus b must equal to 8. And here are constants. Our a minus our 2b must equal to negative 1. a minus 2b equals negative 1. And those gives you negative 1. And now we can solve here. Note that we can solve this one by simply subtracting these two lines from each other. If I take this top line and subtract away the bottom line, I get a minus a is 0. Double negative makes that a plus. So b plus 2b, that'll give me 3b. And again, that's a plus, double negative. 8 plus 1 is 9. And now I divide both sides by 3, which gives me b is equal to 3. Oh, but I know that a plus b must equal to 8. Well, I know what b is now. So that's going to give me a plus 3 is equal to 8. I plugged in my b, and I can subtract my 3 over to get my value of a. So a must equal to 5. So in the end, my partial fraction decomposition is going to be x squared plus 3x plus 1. Notice that's not rational. That's just the polynomial part of our division. But then this rational part, that's the part we decompose. And that will decompose as 5 over x minus 2 plus our b is 3 over x plus 1. Just like that. And that is our result. That brings us to the end of this question, as well as the end of this topic and the end of our lecture here. So if there are any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.